Hey folks, how y'all doing? We are reviewing for the first exam today, and let's go ahead and get started. Um, Problem 1 says to give an example of a graph that is in G, and a maximal matching in G, which is not a maximum matching. So let's say we've got a vertex to another vertex to another vertex to another vertex. Okay, so 4 vertices, 3 edges, and my matching is this edge right here. Okay. Um, that is maximal because I cannot add any additional edges to this matching. This matching cannot be added to. But it's not maximum because I can come up with a completely different matching that has 2 edges instead of 1. And so the maximum I can have is 2 edges. This doesn't have 2 edges, so it's not maximum, but I can't increase this any. I can't add this edge, and because then I'd have 2 edges sharing the same vertex. And I can't add this edge because I'd have 2 edges sharing the same vertex. So this is as big as this matching will get, but I have bigger matchings out there. So that's maximal, but it's not maximum. All right. What does it mean for matching to be perfect? Matching is perfect. Oh, let's make that bigger. Boom. A matching is perfect if every vertex is incident with one edge of the matching. That's what it means. We have literally every vertex is part of the matching. All right. So that's that. Let's keep going. Next page. Prove or give an counterexample if G has an even number of vertices and an Euler trail, then G has a perfect matching. So this is false. So let's go back here. Oh, false. I can do that. And so let's get an example. Let's say I have 6 vertices. Okay. Here's one, 3, 4, 5, 6. Okay. And my edges go, so the top left vertex goes to the 2 in the center. The top right vertex goes to the 2 in the center. The bottom vertex goes to the 2 in the center. And the bottom right vertex goes to the 2 in the center. Okay. So this has an Euler trail. I can go from this middle left vertex to the top to the back, and then over and then back and then around the other triangle. So in other words, I'm just tracing both triangles. And so this has an Euler trail, but it doesn't have a perfect matching, because if it did, the top 2 vertices can only match to the middle 2 vertices, but the bottom 2 vertices can only match to the middle 2 vertices. And so there's no way to match the top vertices and the bottom vertices in this graph. So number 3 is false. A matching is shown in the graph here using red edges, uses Convergence Theorem to show that a matching is not maximal. So the idea here is that we would like to use an augmenting path. that starts and ends at an unmatched vertex and alternates edges. So the only two unmatched vertices are the ones right here and right here. So we have to go from one of those vertices to the other, and I have to alternate edges. So this edge is not part of this cycle, or not part of the matching. This edge is also not part of the matching, so I can't go down. I have to go straight across. Now I have two choices because I can go to either of these two edges because neither one is part of the matching. So it doesn't matter. I could pick either one of them, but I have to alternate edges until I end up at this other point. Once I do, then I can toggle edges. I can include this edge as part of the matching, and then exclude this edge, and then include this edge, and then exclude this edge, and then include this edge. And now instead of having 4 edges in a matching, I now have 5 edges in a matching. And so the number of edges went up. Okay. So that's how the Burgess theorem works. Okay. All right. Let's look at the next problem. 4 men and 4 women have expressed their preferences for one another in the following table. Use the Gale-Shapley algorithm with the men as the proposers to determine a stable matching for the men and women. So, all right. So what we're going to do here is we're going to try to match to S, T, U, and V. All right, let's see what happens. In round 1, everybody approaches their first choice. So J and L both approach S, K approaches U, and I approaches V. So S prefers L over J. Didn't mean to change the color of the text. That's okay. Here we go. Now we can change. S prefers L over J, and so J is not going to be matched up with S because S has a better offer. And that means J has to move on to J's second choice. So now in round 2, J is going to approach V, and we'll see how that works out. Well, V prefers J to I, and so V is going to tell I, no thank you. And so V has to go to V's second choice, which is, not V, I has to go to I's second choice. And so now we're in round 3. And I is going to approach S. Right? And let's see what happens here. S is very happy because I is S's first choice. And so L hits the road. Here we go. And now L has to approach L's second choice, but that's T. And so far, T doesn't have any offers. And so L approaches T, and T is not thrilled because L was T's last choice, but nobody else has proposed, and everybody else seems to be happy. And so I matches to S, J matches to V, K matches to U, and L matches to T. All right. Okay. So let's keep going. Let's look at number 6. Using these preferences, give an example of an unstable matching, and then give a reason why the matching would be unstable. So what if we matched I to U? I is not very happy with U, and J gets matched up to T. J is not particularly happy with T. And then K to S and L to V. Okay, so let's start with that matching. So why is this unstable? So what would be the pairing that would switch off here? So J would rather be with V, and V would rather be with J. All right, so this is an unstable matching. J and V would both rather be with each other. Let's show what's going on there. J is currently paired up with T, but J would be happier with V. V is 2 places higher in J's ranking than T. And V is currently paired with L, but J is 2 places higher in her ranking. And so both J and V would be much happier with each other than they are with their current partners. And so the theory is that J and V would leave their partners to be with each other because that would produce greater happiness for them. Okay? All right. So let's move on. Let G be this graph and X be the set of vertices denoted on the left column and Y be the vertices denoted on the right column. Is it possible to match X into Y? And the answer is no. And the question says then, if no, then explain why not. So the reason why is that these 3 vertices on the left only have 2 neighbors on the right. This vertex can only match to these 2. The second vertex can only match to these 2. The third vertex can only match to these 2. And so there is no way that I can match all 3 vertices into this set of 2 vertices. That can't happen, and therefore it's not possible to match X into Y. Okay? So this is about the halfway point on the practice test. Let's take a break, and then on Friday we'll work through the other half. All right. You take care.